Hey, thank you. Good evening. I seem to have scared a few people off with my subject, or Maurizio did, I don't know, but at least other people have come in. So, my talk will be concentrating on the LHC and everything about it. So you now know the basics of an accelerator, but now we apply it specifically to the LHC and all the challenges associated with the LHC. I try and cover not just the present LHC, but as it was in the past, and as it will be in the future. So just a quick word on high energy physics, to say that this is an international business, high energy physics. It has no borders by its nature. Scientists don't recognize borders when it comes to discussing the fundamentals of the universe. And in fact, by necessity, accelerators for us are also international, because to build larger and larger, more and more powerful accelerators, we are obliged to use collaborations of many scientists, many countries, many funding agencies. And if you look over the last 80 years, you could see there is an exponential increase in the effective energy that we can generate from particle accelerators. So basically, we've been able to keep going more and more higher energy by moving from saturating an old technology, if you like, as far as we can push it, and then leaping to a new one. And the new one over the last 20, 30 years is superconductivity, which has basically been at the forefront of all the high energy particle accelerators around. So here's the LHC. If you come to Geneva, there's the center of the city. You can see our famous fountain. You can also come and visit us at CERN, and you can see the main control room here on the surface. And then you can see the underground areas. The SPS is one of the final links in the chain to produce the beams for the LHC. This is the machine. It's built in the mid-70s. We have large transfer lines that take the beam from the SPS down to the LHC. Each one's about 3 kilometers long. You have, of course, the LHC as well. And then we have the detectors scattered around the surface, 4 major detectors. So in the early 80s, we were at the time building another accelerator called LHC, the Large Electron Positron Collider. We like the word large, since it was also 27 kilometers long. So we were digging the tunnel for that, and a design was prepared to use the same tunnel for a hadron machine, either with or after LHC. The advantage of a hadron machine is the much higher energy that you can achieve with hadrons than you can with electrons. So the LHC had to be designed to fit in the existing infrastructure. We had a tunnel, we had to build a machine to fit into it. So very strong magnets were needed to bend the beam to reach the energy we wanted. And we had to design the magnets in such a way that the two beams of the same type, protons in each case, could circulate inside their own vacuum chambers in the magnets. We used protons in each case because that way we could get much higher collision rates. Eventually we decided, after struggling to try and fit the two machines together, that we couldn't build them together, and LHC was dismantled in order to make way for the LHC in the early 2000s. Just to remind you, you already heard about electron volts. So a car battery, if you attach it to the plates of Maurizio, would give you 12 electron volts. An early accelerator, a Cockcroft-Walton accelerator of the type, Van de Graaff type that was mentioned earlier, about 700,000 electron volts. LHC reached 105 giga electron volts, and the LHC is 7 tera electron volts, just to kind of put it in context. So the history of the LHC at a glance. As I say, history for LHC started with the first papers and the first workshops, discussions, brainstorming sessions, 1983, 1984. In the early 90s, we started R&D, so building the first short models of the magnets and testing them. And then in 1994, the project was approved by CERN Council for construction. During the late 90s and the early 2000s, we placed the main contracts, including the civil engineering contracts. We started the mass production of the magnets. So by 2005, we got halfway there. And in 2006, the 1,232nd main dipole arrived. During that period, we started the installation, and in April 2008, the very last dipole went down into the tunnel, and of course, later that year, we put the beams round for the first time and got ourselves on the front page of Google. During all that period, we were operating another 27-kilometer machine in the same tunnel. So I've gone through all that already. Beyond that, 2010 to 2035, you can see history is a long thing in these kind of projects. So 2010 to 12, we had what we call Run 1. This is where we were running at a reduced energy. This is center of mass energy. It was mentioned before. So the beam energy is half. And this was a precaution because of some problems we'd had during the commissioning of the machine, which I haven't really got time to go into today. We then had a shutdown in 2013-14, and we came back in 2015 at a much higher energy, 13 TeV. That's 6.5 TeV per beam. And we're running like that now until the end of 2018. Then we have another long shutdown, 2 years, Run 3, and then we will come back for the installation of the highly rusty LHC. And we will operate into the late 2030s. Already you can see the time scale from here to here is a very long project. To put it in context, I put a picture of the LHC on Riga. So that, I didn't know exactly where to position it, but this is the main campus of CERN, and this is the scale that the LHC would be if you built it here. I'm not saying the geology is suitable, but if you fancy it, that's more or less what it would look like. Here you can see as well the SPS machine. All the others are very small and are tucked on the main side. So the technical challenges of the LHC. When you design a machine, so we started designing in the 1980s, and we actually switched it on in the mid-2000s. You have to design beyond the state of the art, because by the time you actually come to switch it on, that will be the state of the art. You have to define it. It's 20 years in the future. So long R&D programs were necessary to push the various technologies to the point at which we could mass produce the magnets, the various pieces of equipment to build the LHC. So we've ended up with the highest field accelerator magnets in the world. 8.33 Tesla is what you require for 7 electron volts. Each magnet 15 meters long. It's the largest superconducting magnet system, so there are the big magnets are the ones everybody talks about, but there are 10,000 magnets in the LHC, very, very large numbers of them. It's the largest cryogenic system, requires 150 tons of liquid helium, which would blow up an awful lot of kids' balloons. And we cool 42,000 tons, which is a couple of Eiffel Towers, if I remember rightly. Then we've already, I shall come back to some things later, machine protection system to protect the beam, the machine from the beam and from the energy stored in the magnets. So a few details. You've seen this picture already, the main dipole. This is the interconnect, this is the connection that has to be made between them in the tunnel. So they're brought down individually, parked in position and then connected to each other. During the cool down, LHC contracts by about 80 meters due to thermal contraction, or should I say the individual components will contract, which means that all the parts in these interconnects will stretch apart by about 4 centimeters. So each dipole shrinks by 4 centimeters. And that makes electrical connections and hydraulic connections quite complicated. So it's a very complicated interconnection in this region. And this is what the cross-section looks like with the magnet cold mass inside, all the insulation around. This is the insulation vacuum, and then this pressure vessel which contains the whole thing in position. The stored energy in the beam is a real challenge. So the energy stored in the magnets have got virtually no resistance to electrical flow, but they've got huge inductance. So if you remember your basic electricity, you will know that that acts as a storage. And in the magnets, 10 gigajoules is stored in the LHC when it's running at full current, which is the equivalent of this thing traveling at about 30 knots in terms of the kinetic energy. Now, in the LHC, if for some reason something goes wrong, we have to remove all that energy in about 100 seconds, which is the equivalent of bringing that thing to a stop in 100 seconds, without, hopefully, causing too much damage in the process. The beam for the LHC has 360 megajoules, and that is in a ribbon 89 microseconds long, which is the length of time it takes a particle to go around the LHC, which is the equivalent of 4 terawatts if you convert it into power. We've already had TGV traveling at 200 kilometers an hour, so dumping the beam for any reason is like driving a TGV into a wall, and in this case you don't want to damage the wall. You don't really care about the TGV at that point. So if you do a few calculations, you can see that the amount of energy in the beam or in the magnets can melt tons of copper. So if anything goes wrong, you would very rapidly get a very small thin hole. The problem is that the magnets themselves are very susceptible to the deposition of heat. If for any reason some heat is deposited in the magnets, they will quench. And I can explain a quench to somebody later if they really want to know. The quench limit for the magnets is about 15 millijoules per cubic centimeter. And the beam itself, which is going a few millimeters away, contains 360 megajoules. So you can see that there is a large, shall we say, factor, over factor in terms of the energy available to quench or damage the magnets. And the other problem is that the beam itself is not a solid object. It's not a beam or a P. It's a Gaussian distribution of particles. And so there are always a certain number in the tail of the beam. So you have to minimize the chances that some of the particles that are out here, far away from the center of the vacuum chamber, actually touch the sides. Because if they start touching the sides, the magnets will quench and you'll be in trouble. And indeed, if enough hit, you can damage, you can melt some of the material. So for that we use collimators. Collimators are very simply big blocks that move very close to the beam and protect, so they scrape off the particles on them as opposed to on the superconducting surfaces of the magnets. We need a very sophisticated system for the LHC with, in fact this is wrong, 120 kilometers are now installed in the LHC, and they all need very, very precisely aligning to the beam to within 10 microns. Because they are very tight. This is a picture of our page which shows the collimators in physics conditions, and you can barely see a little white line, which is the gap. It's about 2 millimeters between the two sides of the collimators. So between those 2 points, the beam is traveling 11,000 times a second with its 360 megajoules inside it. So the LHC switched on for physics in 2010, just to mention the 4 experiments that are around the circumference. 2 big general purpose experiments, Atlas and CMS. These are basically designed to see anything that comes off the LHC. LHC-B is a slightly more specialized experiment looking at the B there stands for beauty particles, and it's more tailored to look at matter-antimatter differences. And ALICE is an experiment which is dedicated towards the ion collisions. Hadrons are not just protons. We also collide lead ions in the LHC. So during run 1, we had a good time. 2010, basically, we were commissioning the machine. 2011, we were exploring or understanding the machine, and 2012, we really started production. Now, these numbers probably don't mean very much to you. This is an inverse femtobarn, but to put it in context, the total sum for these 3 years was 30 inverse femtobarns, and that's roughly this number of collisions that took place in the LHC. And as I already said, we were running at a lower energy in these years, but we were still producing very good data, sufficient such that the Higgs particle announcement could come around this point in 2012, and the Nobel Prize rapidly followed afterwards. So just a word on why that's important. Basically, we now know with the standard model of particle physics what matter is made of. It's made of the basics quarks and leptons. There's just 12 of them that describe the universe as the visible universe. And we have a number of force carriers which carry the different forces that allow them to interact together. So we've got the gamma, which is electromagnetism. We've got the strong force, and we've got the weak force that governs the stars. And the missing piece was the Higgs particle in the middle, which basically tells, via its energy field, sets the energy scale of all these different particles. But there's a problem, and that is that the standard model only explains about 4% of the universe. If you look out, you can see all the visible matter. You count it up, as some people do. You work out that there's 96% of it is invisible. And about a quarter of it is in the form of what we call dark matter, things that act gravitationally to change the motion of galaxies, but you can't see it or interact with it. And about 2/3 of it is what we call dark energy, which is even more mysterious, which seems to kind of push the universe apart. So we still need to understand 96% of the universe. And one of our big handles is on the precision measurements of the Higgs particle, because the Higgs particle is one of the keys, the cornerstones to the present set of matter. So in fact, more and more data will be needed in the future to make sure that we can hopefully find something new beyond the standard model of particle physics. So we're now in run 2. Run 2 started in 2015, but we really produced in 2016. So last year we did 40 inverse femtobarns, which means 30% more than we'd done in the previous 3 years, all in 1 year. We had a very good operation with a very high availability of the machine and a very high peak luminosity. This is the measurement of the collision rate in a collider. It's a very large number, 10 to the 34, in units of per centimeter squared per second. The reason it's a large number is that in terms of particle physics, particle collisions, a centimeter is a very large space, and in fact the actual collision area is a tiny spot. We just come out of a technical stop. I just wanted to show you what a technical stop of a big accelerator like the LHC looks like. all these little lines, this is the position around the machine, this is time, December to April, May, and all these activities are going on to maintain and to upgrade, develop the equipment, prepare it for the following run. On an average day in this period, we probably have about 400 people working underground, just to kind of give you a picture. We had two big activities going on. We actually exchanged one of the dipoles in this sector, and we upgraded part of the one of the experiments, the CMS central tracker in this region. Our beam commissioning started in on April the 29th, actually 2 days in advance of our plan, and within 24 hours we were already accelerating the beam to 6.5 DeV and preparing for the physics operation. Since then we've done a massive number of checks, tests, commissioning phases, etc. to prepare for stable beams, and I've not checked today, but we should perhaps be in stable beams now. I have to look on my phone. But certainly very soon we'll start the physics program this year. Looking to the future now, the immediate future, this is where we are, May 2017. We've got this operation this year, an operation next year, with one of these technical stops between. By the end of 2018, we would like to have got in total 150 inverse femtobars. Then we have a 2-year stop, and we come back in 2021 for 3 years of operation, and at the end of that we want to be at 300 inverse femtobars, always increasing the performance. Now, some years ago now, in 2013, there was an update of the European Strategy for Particle Physics. This is when all the scientists come together and they kind of make a plan, a medium-term plan. This is where we want to go. After long discussions in the field, they come out with recommendations which are then adopted by the Council. And their top priority was the full exploitation of the LHC. And they recommended that we produce an upgrade to allow us to multiply the amount of data that can be taken from the LHC by a factor of 10. So that is basically setting the agenda for the LHC in the coming years. Now, you've already seen the CERN complex, but just to show you what is used for the LHC, so we have the source, the LINAC 2. These are the linear accelerators that Maurizio mentioned. Then we go into the synchrotrons, the PS booster, the PS, the SPS, and the LHC. So you can imagine the beam starts here, goes around here, then is passed to the next point, goes to the next one, and then it finally ends up in the LHC. These are the various energies and the size of the machines. And all these machines gather packets of bunches together to form a filling pattern that looks like this in the LHC. So the performance of the LHC is actually determined primarily by what goes on in this lot. These machines at the lower end of the energy scale are really what determines how good the machine, the LHC performs. So upgrades to all of these machines, the injectors are planned, the LHC injector upgrade, and of course a new linear accelerator is being constructed, so that will disappear with a LINAC 4, which with a much higher energy into the booster. This will be connected in long shutdown 2 in 2019. So the goals of the injector upgrade are to increase the reliability, because you've seen we have to operate probably until 2040 or close to it, so we really need to make sure that we've got reliable machines. And also increase the intensity, the number of particles that we can produce to give to the LHC by roughly a factor of 2. And this is takes away some of the limits that we know we've got in our present machines. And all the other programs at CERN, of course, will benefit from these measures as well. Now, in the case of the LHC, if we did nothing, well, first of all, around about 2025, we'd probably stop running altogether, because certain parts of the machine see a lot of radiation from the collision debris. When the particles collide, a lot of things that come off go straight down the vacuum chambers and hit the equipment at the side, and the final focus magnets of the LHC, the inner triplet, they will reach the end of their useful life in this region of about 300 inverse femtobarns. At that point, the radiation damage to the coils will mean that they'll more or less, or they'll certainly become less reliable. If we just replaced like with like and kept on going, we would continue like this, more or less the same amount of data per year, and we could keep on going as long as we want. But the LHC is very expensive to run. So the best thing to do is to replace with a major upgrade, which allows us to increase the amount of data substantially. By implementing high velocity LHC, we'll gain at least a factor 3 over what we could produce over the same period. I thought I'd wake everybody up with an equation. Maurizio had one, so I've got one as well. Mine's prettier than his, I must say. So this equation is it looks complicated. It's not complicated. These are just the basic parameters that determine this thing called luminosity, the event rate. Number of protons in a bunch, number of bunches, the revolution frequency, how often the bunches go around the machine. Gamma is the energy, the Lorentz factor. And then on the bottom, well, you know what pi is, I presume. And the emittance is a measure of the size of the beam transversely. And the beta is related to how strongly we focus it when it goes into the LP. So when we want to upgrade things, first of all, we could try and put more bunches in, but we can't do that because the experiments want a certain distance spacing between the bunches, so they won't let us touch that one. We're stuck with the revolution frequency and the energy. So basically we're left with increasing the number of protons per bunch. And that's a very good way because there's a square here. And decreasing this factor, the beta, by having more and more focusing at the interaction point. Unfortunately, there is a lot of synergy between this number and this number, which means that we also lose out there. So we have to do something about this one, which I'll come back to an explanation later, and we have a mechanism for keeping this number under control. So all these things are interdependent, and it's very easy to say I want to make this thing smaller or this thing bigger, etc. But I shall come back now to the challenges that means in terms of engineering. So one of the goals is to increase the performance of the machine, but to do it in such a way that the experiment can actually manage to take data. Now, during 2012, this is what your average collision event looked like. In fact, there are 25 protons have collided in this. There are 25 vertexes in this case. So it's not a question of a proton hitting a proton. It's 25 in this case. And they have to disentangle this lot. And don't forget, these images are coming every 25 nanoseconds or 40 million times a second. So it takes an awful lot of effort for the experiments to disentangle this, to work out that in this case there is something useful going on. That's these two big lines here, and to store the information. Now for high luminosity LHC, we've been told to limit the number of these events to about 140. We could actually go over 1,000 if we wanted to with the new characteristics. So instead, we will actually actively keep the luminosity lower than we could possibly get, and use it instead to keep the beam longer. The LHC project itself, these are some of the main elements: new focusing magnets, collimators, bending magnets, etc. I will quickly go through some of these things in some detail, including the civil engineering that we have to do. And there are major interventions. It's the largest construction project, accelerated construction project at the moment, with over 1 kilometre of the LHC being rebuilt. And in fact, it's the most complicated kilometre of the machine that we have to rebuild. At the moment, if you imagine one of the experiments here, this is what the LHC looks like in terms of the magnetic elements. These are the final focus quadrupoles. These squeeze the beam to be extremely small at the point they interact. Then you have the separation and recombination dipoles. These objects move the beam apart and then straighten it up again here, so that when it goes into the arc, it is separated by about 20 centimeters. So if you imagine a beam coming in this direction will get bent down into the center, and the one coming in this one will get bent down in this way as well. Of course, we need them in the same pipe in the experiment itself. This is the new version of it. We have a much bigger focusing area, much stronger separation dipoles, and we have these things called crab cavities I'll come back to. Now, the challenge is the crossing angle. In this case, you know, we don't collide head-on. People often think we collide head-on, but because we've got lots of bunches, you would also have collisions in the magnets at either side as well. If I go back, if you collided head-on, you would have collisions right throughout this space as well as in the interaction point. So instead we collide with what we call a crossing angle, where one beam goes that way and the other beam goes that way, such that they only actually cross at the interaction point itself. And in order to do this, you need larger triplet apertures, larger apertures of your magnets than you otherwise would, because the beams are not going straight through the middle, they're going at an angle. And in fact, if you want to increase the focusing, you also need larger triplet apertures. Now, the triplet itself, the present one is built of niobium titanium technology, which is a well-tried standard. It sits here where you could get a good current density with a reasonable field of about 8 Tesla. But for the LHC triplet, we need a much larger aperture. It's more than twice as much. And for that, you need a much higher field in the coil, which means that if you tried to get 12 Tesla here, you would not manage. The superconductor will not work at those fields. So instead, you have to go to a different technology, and we're using niobium-3 tin, which is this curve here, which still behaves nicely out in this region. But this is a very difficult material. We already had a question on it. It's effectively a kind of ceramic, a little bit like pencil lead. It's very brittle. So it's taken a long time. There's already 25 years of development behind it in collaboration with the Americans. And we can now build these kind of magnets. So this is a cross-section of the new inner triplet for the LHC. That's not the only one. There are about 150 magnets that we have to produce for the LHC. They all look very pretty. This is the superconducting, the inner triplet, but we've got a lot of correctors, dipoles, etc. You can see the various configurations. Some of them are very, very a dodecapole. If you ever wanted to know what a dodecapole looks like, that's what it looks like. Now the next challenge is the crab cavities. This is, if you remember the factor F I mentioned, this is the factor F plotted against the beta star, which is the amount of focusing. So the more you focus, the more you go down in this direction. But that means you go down with this factor. So if you ran the LHC, high luminosity LHC, normally you'd be throwing 75% of the luminosity away. And the reason is that because the beams cross at an angle, the effective cross-section is much, much larger. And so it gets worse as you go to larger crossing angles. Or it gets worse as you get smaller and smaller, thinner and thinner beams. So you have to do something about it. The clever trick that we've come up with is you install a piece of equipment that it's one of these RF cavities again, but it produces a different kind of kick. And it can kick the head of the bunch one way and the tail of the bunch the other way, such that they kind of skid around and they effectively cross head on. And then when they come out the other side, you kick them back so that they behave normally again. So that's it's like a crab. That's why it's called a crab cavity. It makes the beam bounce sideways a little bit, and it can overcome this geometrical reduction factor. The problem is that these are very complicated beasts that have never been used in a hadron machine before. And in fact, we have a big R&D and test campaign, and we will install some of these in the SPS next year in order to confirm that they indeed do what we show. Collimation is another big challenge. Just to say that, as I said, the core of the beam it contains most of the energy, but there is a lot out here in the halo. In the LHC, about 25 megajoules in the halo, and the collimators here have to basically clean up this area. So you have a primary collimator very close that hits the beam, the primary beam, and then you have a number that take away the secondary and tertiary halo, and you're trying to protect these objects out here. The collimators themselves, as we go to higher intensity, you need more robust materials, and we're now looking at rather exotic materials, copper diamond composites and molybdenum graphite jaw composites. This is a molybdenum graphite jaw, are being tested because these should be able to resist more the very, very high energies in the beam than we can at the moment. The civil engineering, there's a lot of civil engineering to go on because all the new equipment will have to sit inside, underground in the tunnels, and we build a whole new set of tunnels to house the equipment. So this is what it will look like. The blue part is new caverns and tunnels that will have to be built, and all this part, this is the experiment here. All this part will have to be rebuilt. This is all new equipment that, so the inner triplets, the D1s, etc. Very large amount of work. And by the way, we also will build superconducting links, which will actually allow all the current that we need to feed these magnets to be brought from up here downwards. And this is a technology that uses high temperature superconductors. So the project was approved in 2016, 950 million francs, whatever that is in euros. What,
more or less the same.
These days, more or less the same, I guess. Almost $1 billion and 1,600 FT years. And over the coming years, over the next 10 years, you can see we're going to be spending a lot of money. Looking further, so here is where we do the LHC ejector upgrade. Here is where we build high luminosity LHC. It will take about 2.5 years to change that 1.2 kilometers of machine. And then we go into a period of running right out into the mid-2030s where we're actually exploiting the LHC. And that just puts it down in terms of the activities. So we are now in the phase of preparing specifications, going out for tender, etc., for a number of pieces of equipment, including some of the major pieces of equipment for the high luminosity LHC. Even though we're only going to install it in 2025, we have to start ordering it now. And then we'll run at least the 10 operational years, if not more, in order to reach the 3,000 inverse femtobars that we would like. Now, somebody mentioned energy earlier, so you get my second equation, which is a bit simpler than the first one. What about the LHC beam energy? Because we started at 7 TeV center of mass, we went to 8, now we're at 13. So first of all, how is the beam energy determined? I've got a very simple equation. The beam energy in the LHC is the product of these three factors. One is the speed of light. The next one is the average bending radius in the arcs of the LHC, which is 2.801 kilometers, if I remember rightly, and it's set by the tunnel itself. You can't go outside that. And then the third factor is the magnetic field of the dipole magnets. So you put them all in together, and you can easily get the 7 TeV. Now, if you want to increase the beam energy, you can't do anything about the speed of light. You can't do anything about the current. It's already there. So all you can do is increase the energy, the magnetic field in the magnets. You can push the field in the existing magnets, or you can install new magnets. If you want to do anything else, you wait and you'll hear from Daniel Schultz the alternative, which is to do that, and then you can get a real jump. So the first thing is, when are we going to run at 7 TeV? Now, the problem with superconducting magnets is that they often need to be trained. They need to be taught to work at very, very high fields. So when you lift them up higher and higher, the actual mechanical forces generated by the field is trying to tear the magnet apart. And if for any reason something moves slightly inside the magnet, it only has to move by a few microns, the magnet will quench. But then it'll settle into a new position where it's happier. So the next time it will go higher and higher. So this is called training. So this is the training campaign we did. So it took 50 quenches to reach 6.5 TeV in one of the sectors. So quite a lot of effort, especially as it takes you several hours to recover from a quench afterwards. We will go to 7 TeV after 2021 because we need to do a little bit of work on the magnets themselves to make sure that we are really safe with all these quenches. We're now studying running the LHC at an ultimate energy, so the magnets can actually reach 9 Tesla, not 8.3. They were all tested to 9 Tesla, so in principle we can all go there. And so we're going to identify what we can do to run at 7.5 TeV or 15 TeV in the centre of mass. It will need some effort, and it will mean that we're running the machine really at its absolute limits. So we've no idea what that will look like at the moment, but it could come in the 2030s. There's no promises here at this stage. Now beyond that, there is an idea. In principle, we could exchange a third of the dipoles with stronger magnets. So you just take out the middle magnet in each cell and replace it with one of these, which is 11 Tesla magnet. Now the advantage of that is that it would allow an extra TeV, it would allow 16 TeV collisions. And we have the technology, we're building these magnets, or something very similar, for the Highland Rusty LHC project. The disadvantage is that the geometry of the machine would be very different because you'd have a much stronger field here than you have here, and it would distort the orbit and you would need some correctors. Loads of other equipment would also need upgrade, and it would essentially mean rebuilding the LHC. So I think there it's a massive effort for a relatively small gain. So you wouldn't contemplate it anyway until Highland Rusty LHC is complete because it would take us several years to fix it. So we've not really made a serious study there, but it is a possibility. The last possibility is a high energy LHC. So here you simply take out the present LHC, you build one using stronger magnets, and we settle on 16 Tesla dipole magnets for the moment as a working hypothesis. In this case, you also have to rebuild the SPS for a higher energy, otherwise you can't reach an energy that's high enough to inject into this machine. And of course you need new transfer lines to transfer between this higher energy. So it's a new machine. It's a different set of equipment using stronger magnets that will be developed as part of the FCC R&D. And it would act as a test bed for what Daniel's going to talk about later. It would allow 27 TeV collisions to take place, so almost double the LHC. So it would have to come after high luminosity LHC, but it could be something that we do in the future. Okay, it would also need SBS and transfer lines. Now, one minor problem is that the present design of the magnets for FCC looks a little bit like this compared to the LHC, and we've got a fixed size tunnel. It's only 3.8 meters diameter, and it's not clear that we can fit it in. The last thing I got was, it just about fits, I think, was the answer I got from somebody. So this is a cross-section of the tunnel showing the high-energy LHC magnets, how they would fit. And you could just about get past it in order to install it. And there's a preliminary parameter list in case anybody's interested. Things to note: stored energy in the beam, 1.3 gigajoules. It would be a little bit like I don't know, a jumbo jet or something like that. And the number of events per crossing is huge as well. So it will be a challenging machine for the physicists and for the engineers to build. So there's my summary. So the LHC covers over half a century already, and it's pushed really technologies beyond the state of the art at each stage, and is continuing to do so. And we've now got a plan to keep us going until the 2040, let's say, and we even start looking at possibilities beyond that to upgrade the machine even further. So